Good morning, everybody. Should I give it another minute? Okay, so we're going to get started, okay? Lunch is in the back. Awesome. So, today we have Dr. Jeramie Adams, who is the Vice President of the Renewable Upcycling, Carbon Materials and Asphalt Technologies Research Group at the Western Research Institute. With a career rooted in deep chemical expertise, Dr. Adams oversees the development of proof-of-concept processes designed for industrial scale and validation. A talented chemist, Adams earned his PhD in chemistry from the University of Wyoming in 2008 and continued there for the next 4 years as a postdoctoral researcher before joining WRI in 2012. At WRI, he has established a distinguished track record of leading high-impact commercial, industrial, and federal initiatives. As a central figure in energy and materials research, Adams has spearheaded several major research consortia and Department of Energy projects, most notably the Consortium of Affordable Carbon Fibers in the USA. His extensive research portfolio spans the entire hydrocarbon life cycle, from stabilizing problematic crude oil emulsions and mitigating heat exchanger fouling to advanced co-processing of petroleum, coal, and biomass. Adams is an integral part of the collaborative carbon engineering research being conducted at SCR's Center for Carbon Capture and Conversion to find alternative high-volume uses of Wyoming coal. He is the co-lead on the downstream project that utilizes feedstock derived from CCCC's solvent extraction technology to produce coal-derived asphalt. Please join me in welcoming Jeramie.
All right, thank you, Trina, for the introduction. And so my main goal really today is that I want people to come away really with a different view of coal, if that's possible. You know, coal is a 4-letter word, but it's not a dirty 4-letter word, okay? So I hope that by the end of this, that this is something that you will take away. So I'm very grateful to be here, very grateful also to this university, and also getting to continue to interact with this university. So there's a couple folks here in the audience that I would like to acknowledge. So we have Dr. Cheng-Yen Pan. Can you throw your hand up for us? He's been involved in this project. He's a PhD organic chemist, a very good chemist. He's helped a lot on this project. And then I also saw Dr. Elsie Mueller. Where is he? I saw him somewhere. There's his hand in the very back. So he's been involved in this project also for several years. So he's also a research scientist with UW-SCR. And then, of course, support from SCR and Trina as well throughout the years. So, you know, can coal be used in a way that makes sense? And so we believe so. We've made a lot of progress. And so I'm going to kind of share a little bit of the overview of, like, what is the situation of coal a little bit, because it's an abundant resource in this state, but many people don't know much about it, and especially many of the younger folks. So Powder River Basin coal is a major resource for energy in our country, and we can see here on this plot is showing the production from the peak in 2008 to what it is today of coal, and this is in millions of short tons. So we've went to something like 450 million short tons, down to less than half that. And I don't know for you, but when I think of energy, I never realized like the volumes and how much we consume of energy. You know, just to think, this is not all the coals that are used for energy. This is only one source of coal from one mine out of Wyoming. So to think 450 million tons, that means every year we could drive to your house and we could dump a ton of coal out for you, every man, woman, and child in the United States. You know, and this is just one energy source. And so, you know, just to try to wrap our mind around this, you know, how big this resource is. Of course, this has had a pretty big impact now. And why do we see this decline? It's because we're retiring coal-fired power plants. You know, they're more and more are going offline, and a lot of it's driven by environmental concerns. And we've done a great job with trying to address some of those concerns and bringing on renewable energy. Wind is now huge. It's like 12% of all the energy produced in the United States. There's solar, there's different alternatives. And those things, they're all great, but they, it does have some other impacts. Overall, Wyoming, the Powder River Basin coal, out of all the coal that gets used for energy generation, is more than 43%. And it's been in the 40% plus range for a very long time. So it's very important to the energy of our country, and it has been for a long time. And of course, locally, this has a significant impact, on the state as we begin to use this resource less and less. It means less and less revenues for the state. So the revenues have also dropped by more than half for this resource. So the question I pose is, should coal be used? Can it be used in a way that actually makes sense? Can there be any chance of a positive environmental story? Because I remember getting involved with this, and many people came to me and they said, this is ridiculous. Coal is dirty, leave it in the ground. That's the best thing you can do with it, And so I was not convinced. So if we look at coal versus other kind of fossil fuel resources and actually look at it not in the aspect of burning it, because we're all familiar with the CO2 emissions after you burn it and you generate energy. But if we look at the resource as far as taking it out of the ground, this extraction process, and then what's needed to transport it somewhere that you can actually use it for energy or turn it into something useful, this is known as cradle to gate when you do like a life cycle assessment. And so there's a certain amount of emissions that are generated with that, which has to do with the fuel and the energy, to do that extraction and transportation. And so it turns out that if we look at Powder River Basin coal, it has about 90 kilograms of CO2 per ton. And that's actually quite low compared to crude oil and natural gas. Now, granted, there's great variability in, oils and in natural gas, but PRB coal, it's very well known. These values have been studied, and it's very consistent. Crude oil is a little bit different. We have this average value of like 175. It can be lower. I just say that just for full disclosure. But in many cases, it's much, much higher. And then if we take upgraded material from Canada, it's even greater than 500. So, and then if we think about natural gas, and if we want to use natural gas to make materials, especially materials based on carbon, it actually has a pretty high footprint. And again, crude oil and natural gas, a lot of this has to deal with, of course, there's the extraction, but there's a lot of pumping of this material, but then there's a lot of flaring of the methane, and that's where a lot of this, and also leaks in the case of natural gas, and that's what contributes to these very high CO2 footprints in this kind of cradle-to-gate scenario. So this is something that most people have never considered, but when you're thinking about making new materials, it's something that we should consider because the world is getting more and more concerned with, what is the carbon footprint of the materials that we're using. The other thing is, how does it kind of compare to other materials? So limestone is used in a lot of construction applications. It's just mined right out of the ground, and so there's, some processing, crushing, digging it up, transporting it. So the cradle to gate for that is about 25. If you look at pine that's used to make lumber for building houses and for making plywood and the studs and all these other kinds of things, it's about 90. And then if you compare that to Powder River Basin coal, it's almost the same, which is something that's kind of interesting, that it's not this scary thing if we want to use it for these other kinds of applications. And then of course, if you want to use cement, it has a huge carbon footprint, and that's just because of the chemical processes and the high temperatures, and you release CO2 when you make the different components for the cement. So, it's really no worse than if we want to just use, like wood. So I think this was something that was very interesting. Also, coal has a long history of being used to produce all kinds of different materials and as a chemical feedstock. It was used actually before petroleum, and many things were made out of it. And then once petroleum came on board, it was cheaper and easier, and it made sense, so a lot of these things kind of got shifted towards petroleum. But coal, I mean, it's been used, but this idea of using coal in this way has been lost. We just don't think about it anymore. So our particular interest at the Institute is trying to make an asphalt binder out of this. We have a very long history. We've been involved with a lot of federal projects for many, many decades. And why do we care about asphalt? It's kind of boring. Everybody drives on it. You take it for granted. You never think about it unless you hit a pothole or something like this. But asphalt, it's one of those things that's a very high volume market. So it's about 100 million tons worldwide, or 30 million tons in North America. And asphalt, I'm just referring to the black sticky stuff, the glue that holds the rocks together. And asphalt is actually, it's a very circular material. It's the most recycled material in the world. You can see here, here's some milling. They call this milling, where they grind up the top layer and then they mix that with some fresh asphalt, and then they put it back down and redo that section. And so it's such a high volume, it makes sense. We have to use it and continue to use it and reuse it. We're not going to landfill that volume of material. So, this is something that most people also don't realize about asphalt. 94% of roads in North America are paved with asphalt, and it's a market that is increasing. So the annual growth rate, is something that it goes up every year. It's not something that goes down, because there continues to be construction, but you have to do maintenance and keep up and redo your roads and all of these kinds of things. Now, there has been a big change in the industry, in the last several years, due to the last administration that was very concerned with environmental impacts of different industries that are known to have kind of high carbon footprints. And so there was some new rules put out by the federal government, which are kind of buy clean policies, which means you need to buy something and use something that has the lowest carbon footprint. And so they're going to determine that through an environmental product declaration. And it's an EPD, and basically it's a nutrition label of the different environmental impacts of your material. And so the main thing that they're concerned with is this here, the global warming potential. Basically, it's the kilograms of CO2 equivalents. And so basically on a federal project, they're going to have to say, show me your EPD and the one that's lower, and if it doesn't cost too much more, they're going to have to go with that. Now, several states also have buy clean policies, Colorado and some on the West Coast and on the East Coast, and it's becoming a popular thing. Also, the Federal Highway Administration, which is FHWA, they have been very active in doing all kinds of different climate change projects as well, trying to understand how we could improve the environmental impact of the paving industry. So where does asphalt come from, and what's kind of the current situation? So petroleum-based asphalt, it's just a byproduct of the refining process. So you have crude oil, goes into a big distillation tower, it gets heated up, and you collect all these other fractions for fuels, for lubricants. Some of it goes to chemicals, goes to all kinds of things that we use every day. And what you get at the end, after you distill out all of the good things that are higher value things, you get a kind of a black sludge at the end. And this is where the asphalt comes from. And so not all crude oils can make an asphalt. And it's about, of all the crude oil, about 2%, can actually make an asphalt. So this is a byproduct of the refining process. They don't intentionally refine crude oil, and they're not ever going to intentionally refine crude oil to make more asphalt. So as long as this whole situation with producing crude oil for fuels and everything is going well, we'll have asphalt. But what happens if we begin to close refineries and we begin to have alternative sources of energy and alternative fuels? We begin to lose some of our production of asphalt. And so there have been many refineries that have shut down or converted to renewable diesel. So in this state, we used to have an asphalt plant and a refinery here in Cheyenne, which was the Holly Frontier. They completely converted to renewable diesel, and so they don't produce asphalt anymore. But there's been many plants that this has happened to. So the supply of the asphalt, it has been going down. And obviously, we know this market isn't shrinking, so we need to make up for that somewhere, and we make up for it by doing imports. And so imports for asphalt have been also increasing. And in a broader context, the Asphalt Institute Foundation, it's basically a group set up by all the suppliers of asphalt, so the Exxons and the different companies that basically large oil companies. They, of course, they're looking into the future and how things are going to look. They hired Wood & McKinsey, which is a firm that is very well known and respected in the energy sector, to run a study and say, is asphalt supply really going to be under threat in the future? So this was just published last year, and they looked at the overall picture here, and what you see are kind of these three lines. One is base case, which means we just do business as usual. We don't think about the energy transition and switching over to renewable fuels and energy and all this kind of stuff. And what you see is that they kind of expect a peak maybe 2030, 2040. They're revising these numbers now because of the new administrations and new policies and new ways of thinking, but there will be a peak at some point. And then a lot of countries have made pledges to reduce their carbon footprint. And so if people actually keep to their promise or their pledges, we'll see that you'll have a significant decrease in available, in the use of oil into the future. And then if we actually go with the net zero case, which has been proposed, and this is all the things we need to do to meet net zero, we're going to have a much more significant decrease in oil demand in the future. But if we look at just the asphalt binder, of course, like I said, the binder comes from the petroleum. If we look at the North American market case here, what they said was by 2040, we're in a situation where supply, which is that little yellow dot up there, is the demand. The supply is basically going to meet demand. There's not much wiggle room. And then they said, if we meet some of the pledges, or if we meet all the pledges, we have this other bar over here in the red, where we see a situation where all of a sudden supply is not going to meet demand. And so this kind of got the industry kind of worried and thinking, what are we going to do into the future for supply? And just remember that, again, yeah, we can increase supply, we can do, process some more stuff in a refinery, they have some capacity there. But the thing is, unless they're going to sell fuel, they're not going to just increase capacity because they sell the fuels. The binder is the byproduct. So can Wyoming coal increase asphalt supply in a cleaner way? So if we look at crude oil and we look at the carbon footprint of the asphalt, that most of the carbon footprint, over half of it comes from the crude oil and half comes from the actual construction process because you've got to do all the heating and transportation and all this other stuff. But if we look at just the crude oil portion, which is the extraction, which is that big blue section, and then the little yellow section, which is the transportation, that accounts for a significant amount of CO2 emissions, so around 430. So this has been well studied by the National Asphalt Pavement Association. And if we then were to think about inserting coal into that space, granted, we have to do some things to the coal, but if we use the coal and we say, okay, if we just use it for the extraction and transportation, we can see it's already going to have a much lower carbon footprint to begin with, so up to about 5 times less CO2 emissions. So it does, maybe it makes sense. Maybe we should try this. But there are also other practical benefits to using coal. One is that if we think about Powder River Basin coal, it's a massive resource, 25 billion tons of economically recoverable coal. So, it's at the surface, it's big, thick seams, it's something easy to get at, it's a domestic feedstock. We don't have to worry about if someone gets upset at our friends across the border, what's going to happen to our supply. And so the thing is, if we think about paving in North America, just from one coal reserve, which is Powder River Basin, we could basically pave almost 1,000 years of roads with this material. So, it would be, if we could figure this out, we'd have a very strong, long-lived, consistent supply. This is important, also the thing to realize, since asphalt's a byproduct and crude oil slates at the refineries are always changing, the asphalt consistency is always changing too, and it's a big problem for them to kind of figure out how to deal with this and make good roads. That's part of the reason we don't have as good of roads as we used to in the past. The other thing is it's not a very mature coal, so we don't have these kind of cyclic aromatic compounds, these polycyclic aromatic hydrocarbons, PAHs. These are carcinogens. It's a big concern for the paving industry, especially for workers out there on the road. There's a long history with studying these in this industry. Also, since we're not going to look at this as a byproduct and how can we use a byproduct, we can actually begin to think about it doing something intentional. We can tailor make materials. We can engineer properties we want in it for different climate zones and applications. It's a very consistent feedstock. The chemistry is very consistent. It's also low cost, $15 a ton. There's not many things that you can buy on the planet for $15 a ton. But it's also one of those things that it's highly mobile. It's already got rail infrastructure that goes all across the country. So when people think about big projects, you know, infrastructure is one of the things that can kill a big project right away. I mean, there are oil companies that I've met with that they like Wyoming oil, but they said, there's no roads. We're never going to pay the millions of dollars it takes to put in the infrastructure and roads, and so we're not going to go there. So this is something that's already not a concern when we think about using coal and using it for other applications. So coal, obviously, most people know, it comes from dead biomass, particularly plant matter. And the thing is, it goes into the Earth's crust, and so the Earth, in that situation, it's exposed to heat and pressure and time and all these things. And so that does a lot of chemical transformations, and that has a big impact. And you can actually get different ranks of coal depending on how long it's been in the Earth's crust, and you know, there's different things that play into that. But there are these different grades, and basically as you go to more mature coals, which have had more time, more temperature, more pressure, they get more carbon content in them, so more carbon rich, and that's kind of what's shown on the bottom here. Wyoming Powder River Basin coal, it's subbituminous, so it's not very mature, and in its chemical structure, so I'm a chemist, so I apologize, I'm going to show you some chemistry. So on the least mature coal is lignite. It looks kind of like lignin, so this biopolymer that's in a lot of cellulose type materials. And so as it matures, you know, it goes through some chemical transformations. It becomes more aromatic, a higher carbon content, and then it starts to lose a lot of the oxygen content along the way too. The thing that's nice about the subbituminous coal is that it's not these little tiny molecules, they're still kind of large. You have some aromaticity, and then you have these nice oxygen groups that you can do some reactions with, so these OH phenolic groups. So the idea was, okay, let's take coal and let's see if we can do a coal refinery. Because a petroleum refinery doesn't really have a lot of waste. They try to use all parts of the crude oil. So we would like to do the same thing with coal, and there's different ways to do that. There's a combination of processes that will help us use all the different parts of coal. And so I'm not going to talk about necessarily all of these different aspects, but I just want to put that out there that, you know, that the whole idea here is not to waste anything of the coal, not to create any other waste feedstocks or waste byproducts where you have tailing ponds and then you have environmental issues because of that and all kinds of things like this. So can we actually get asphalt from coal? You know, as a chemist, I look at this and I think about it and I'm like, okay, this seems kind of challenging. Coal is a solid for one. It doesn't really have a property of an asphalt binder. It's not a sticky thing. And chemically, it's just this big conglomeration of these huge macromolecular structures. So right now, I came with a background of asphalt, understanding asphalt chemistry, which is also a huge kind of mess. It's hundreds of thousands of molecules, all different kinds. You have very hydrogen-rich things to very hydrogen-deficient molecules that are very aromatic. And so it's this complex mixture of things that all have this nice interplay that makes a really sticky material. And asphalt's viscoelastic. And so what that means is it's not an elastic solid at room temperature. It's soft, you know, it's pliable, and then you heat it up and it becomes softer, eventually it becomes a fluid, a liquid, a Newtonian fluid. And then you can cool it way, 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 way down to like minus 30, minus 40 degrees C, and then you have a glassy solid, you have an elastic solid. So, you know, the properties, you know, what is it behind asphalt that gives it all these interesting properties that it can be viscoelastic? Because on an asphalt pavement, you need that because you have high temperature days and you have cold temperature days. If you have something that's going to set up and be a glassy solid on a low temperature day, what is that going to mean? It means it's going to crack on you. So, you know, it's not a secret. It's been known for a long time that you can actually extract smaller molecules from that larger coal macromolecular structures. And so one way to do that is with solvent extraction. And so we can actually do that. But the chemistry of those molecules, again, They're very polar, they're very high melting point, and they're completely incompatible with asphalt. And one thing to realize about asphalt, since it's the most recycled thing, if we come with a product, it better be compatible with asphalt because we're going to be recycling it with petroleum asphalt for a very long time into the future. So the properties are all wrong. And this material basically, it behaves basically like a glassy solid. But if we look at the molecules again that's in petroleum, we see that there's obviously some differences. There's differences in oxygen, in heteroatom content, and what those functional groups and those heteroatoms look like. But in petroleum and all those molecules, there's usually a lot of long kind of alkyl groups that are there. And so I look at this, and from my background, I say, okay, well, I got to put alkyl groups on these aromatic molecules. And how are we going to do that? So the basic process, just high level, is we're going to take coal, we're going to do that solvent extraction part, which is going to give us those monomers with all that oxygen. When we do that, we do it in a way where we get a very high conversion of the coal. We're talking 75 to 85% conversion of the coal. So there's a little bit of leftover. That leftover, is not a waste that has to be, backfilled in a mine or put in a tailing pond. It's something that goes into other processes, which SER is also developing, which I'll just touch on briefly at the end. So those can go into things like building materials and soil amendments. So how are we going to get, to this situation where we can make a paving or roofing grade asphalt? Because I didn't mention, but the shingles that we have on our houses, 25% by weight of that shingle is asphalt binder. So we tried many things over the years, and one of the things that we found that works really well are alcohols, a whole wide range of alcohols. Alcohols, of course, can be petroleum-based, they can be bio-based, they can be renewably sourced if you want. And what that does is breaks down, again, that large structure, gives us these molecules. And what we've done is we've looked at the alcohol. We've also figured out a way to take anything that happens with that alcohol and create value out of it. So we're actually creating some co-products that are quite valuable that help offset the cost to do this whole process. And I'm not going to go into detail what those are. So remember the challenge. I was thinking, man, how are we going to put on these long alkyl groups to help give it the right properties to become a viscoelastic material? Well, we need also to think about high volume solvents here, because if we're talking 30 million tons, we got to have something that makes sense. Well, one thing that could make sense is that, there's quite a bit of plant-based, animal-based oils available. And, there's already a huge industry to take those, collect those, extract those. And what we found is that we can actually use those. We can use those, particularly the fatty acids, and we can put them in a process that's relatively low energy. We don't need hydrogen. We don't need catalysts. We're not generating any extra gas in this process. And then we actually add some biogenic carbon into our product, which, has some additional benefits, especially if we're looking into the future. So if we take a kilogram of vegetable oil fatty acid and we use that in a product, you're going to store basically for each kilogram 2.8 kilograms of atmospheric CO2. So we kind of like this concept of marrying, fossil fuels with kind of something from the bio side of things. And so we did these reactions, and we do end up getting a material that is now this nice, beautiful viscoelastic substance. It's quite sticky, so it looks like it has the physical properties that we want. Also, this is just showing you the material before and after the reaction in toluene. Before doing this reaction with the fatty acids, it's not soluble in toluene. Afterwards, completely soluble. So we really changed the properties of this material. And asphalt binder itself is completely soluble in toluene, so that's good. We react almost all the OH groups on our coal molecules. It's a very high conversion, this process. We can recycle any extra solvents. And more importantly, we make the right grade of materials that we want. So we're making what's called a PG52 minus 40 and a PG72 minus 22. So those are the kind of the grades of asphalt. Those two numbers stand for the high temperature end of your asphalt, kind of the climate you would use it or the traffic load. And the negative number is the low temperature of a particular climate or region. So the United States is huge, so we have cold climates in the north, hot climates in the south. And so, it's great that we can tailor make materials to meet kind of all of those climate ranges. Also, depending on how we do it, we can change the amount of biogenic carbon that's in our product. And again, this is just showing some of the different products that we've made. So we can make materials that are kind of soft, that would be good for paving applications, again, low temperature, high temperature climates, and then we can make very stiff materials that are good for roofing shingle applications. So this one is I guess, a bit technical, but this is looking at the rheology of these materials. So what I did is I took a typical Wyoming asphalt binder and compared this to those two products that we have, like a low temperature asphalt and kind of a higher temperature asphalt. And we looked at the rheology. So we're looking at how does this material respond with temperature as far as how viscous is it or how elastic is it. And so we sweep this over all kinds of temperature ranges. So this data is going from -30 down to +45. And what we're looking at here, on this axis, this is the complex modulus, so it's very stiff when it's cold. That makes sense. It's getting more and more solid. And as you warm it up, it's less stiff. And then there's kind of a theoretical limit. This is where you would think of a glassy modulus, so that material, when you cool it all the way down, will become a glassy solid. And then on this axis here, this is saying, okay, because this is a test that's an oscillating test, and so if basically if you're not moving your sample at all, your phase angle is like 0. If you move it completely, then it's going to be completely fluid, a phase angle of 90. So that's what this axis represents here. So up in the upper left hand, we're more of a solid, very stiff. As you warm it up, then it starts to get softer and softer, and it gets more fluid-like. So this tells us a lot of properties about the asphalt binder. The thing I want to point out is that the petroleum-based binder is very similar to the coal-based binders, and this is a kind of an unusual result. It's actually hard to do this with engineering asphalt binders. The other thing that is interesting is that these materials become a little bit softer, a little bit more fluid as you heat them up. We don't know for sure, but this may have additional benefits. This could lower the paving temperature, which is a big issue in the industry because they're trying to lower their carbon footprint on the building of the roads. And you could get better compaction because when you make a road, they go over it with the steam rollers for a reason. They got to compact it and get at the air voids because that can cause some issues with oxidation, with moisture, and all kinds of things. So there could be additional benefits to this material. This is one of the big problems that we encountered, which is a huge hurdle that took us some time to overcome, is the oxidation behavior. Because asphalt sits on the pavement, and over time it becomes brittle because it's just oxidizing in the environment. And it just stiffens. It loses its ability to relax stresses. So you have thermal stresses when your material heats up and it cools down. And then also you have traffic load, which is constantly stressing it. If you can't relieve those stresses, you're going to crack. And so we want material that's not going to age any worse, hopefully age better than a petroleum asphalt. So this data here is looking at the different chemical classes of chemicals that are in our product. And so I'm not going to go through all of these. The main thing is that you see that there's some over here that we call maltenes, and then there's some that are called asphaltenes. Asphaltenes are kind of like the particles suspended in solution. And it's very normal in an asphalt that you take some of the liquid phase. As it oxidizes, it comes part of the particle phase. So that's a normal thing that happens. And so this total is the sum of these three things here. This is basically the total of the particle phase. So this kind of particle phase, when you take it unaged, and before we ever put an asphalt down, we intentionally oxidize it. So these are standard specifications that all DOTs have to go through. You take your material and you oxidize it, and then you look at the properties after oxidation. And hopefully we don't see a huge jump in the properties before and after oxidation. And what we see is that this change is pretty small, actually, 3.4% change. That's similar to very good petroleum-based binders. A lot of binders will change 8, 9, 10%. So we're getting very small changes, and then we see very small changes in the rheology and other behavior. And a lot of alternative binders, especially bio-based ones, they're super oxidation sensitive, so they change a lot, which is bad because you leave it on the road and then it doesn't last very long. And for me, this was amazing that we could overcome this challenge because I don't know if you know, but Powder River Basin coal is full of water. And then once you dry it out and you can put it in a silo or use it in a lab, or you can dry it out really well and you can pull it out of the oven, it might smoke on you. And in some cases, it can spontaneously combust. because it really wants to react with oxygen. So by doing the chemistry that we've done, we've mitigated this problem that's kind of inherent to these coal molecules as well. So we've been able to produce larger quantities of some of these materials. This was produced at a pilot plant. This material was then given to the Wyoming Department of Transportation, where they made what's called a mixture. You put it with all the rocks and everything else, because that's what really gives the material, the stiffness and the strength is all the rock and everything. Because the asphalt binder in your pavement is only 5%. So they did all the, they made this, they compacted it, they said it seems like it works great. One benefit is it didn't have any smell. They were super surprised because asphalt always has this kind of sulfur smell. The other thing, if we look at this product, which I thought was, this wasn't necessarily the intention of what we were trying to do, but it's something that came out of, of what we were doing. This idea of marrying kind of, some biogenic carbon with the coal. If we look at that, this particular product here was about 40% biogenic carbon from our vegetable oil reactive solvent. And if we think about, if we took and replaced 25 million tons of asphalt that's used in the US, and we paved everything, so this is best case scenario, with it and used it for all the applications, this would be equivalent to 5 million cars emissions in a year that could be stored in the pavement. So this could be a way to sequester CO2 in the long term. And so, and I'll just be honest for full disclosure, one of the issues in all of this is the economics. And the economics, because it's hard to compete with a waste or a byproduct for petroleum refining in these huge volumes, and now you have to engineer and develop a new product, and that requires some chemistry, it requires this vegetable oil-based solvent. And when we started this, it was looking, yeah, it looks pretty close, but then in the last years, there's been this huge competition with vegetable oils going towards renewable fuels, so renewable diesel. So that's been driving the price up, and so, one thing I just throw out there is, maybe what is the best way to use vegetable oils? The vegetable oils, they're continuing to increase like crazy, but the demand is just going to fuels. Obviously, it's great because you're taking that CO2 and you're just recycling it from the atmosphere, goes into your renewable diesel, and you burn that, and it just goes back in the atmosphere, and you just kind of create this cycle. It's not a net zero cycle because there's a lot of energy and emissions just growing the soybeans for the oil and harvesting it and fertilizing it, doing all these things. But it's much better than just flat out fossil fuels. But we also know we have other alternatives for transportation fuels, especially for cars. We have electric cars now and all these things. But if we think about it, what's the best use of these vegetable oils in the future? Is it really fuels, or should we maybe focus on materials? Because if we use it for materials, then it's something that gets locked into like a pavement, and it will stay there for potentially hundreds of years, at least 100 years easily. So this is not, we're not doing fundamental research. We do a lot of applied research. We're trying to make products that will actually be commercialized and get to market. And at the Institute, we are almost fully commercially funded. We do some federal projects, some state projects, but really we're commercially funded. So we interact with companies all over the world. We've worked with 3 different companies that are in the emulsion space, because you'll see here in Wyoming, it may just be super annoying when you're like, oh my gosh, I'm driving on this road and there's all these rocks flying up. What the heck happened here? They make an emulsion, they coat the road with an emulsion, and they put the rocks on it. It's called a chip seal. This is something that helps the road last for much longer. And so emulsions is a huge portion of the asphalt industry. So anyway, these companies, they were excited, they wanted some, we sent some, and they're the experts in the world in making emulsions. They looked at it and they were excited, and they're like, send us more, we want to continue to work with this. Also, roofing companies. We have 8 roofing companies that are asking for samples. We've sent samples to a couple of them, and this is some feedback. As they said, either way, we're excited. This is the results that we're seeing here, and they're like, can you send us production quantity samples, because we want to continue to test this. We also have multiple paving companies that are interested, and we were asked to enter a competition by CRH Ventures. CRH is the largest road contractor in the world. They did a venture capitalist type of thing where they asked for all kinds of technologies, and then they selected a few to fund to go further. They had 120 applicants, and ours was one of the top 10 Unfortunately, we didn't make it of the two that they picked. But just to say that what we're doing here is not just, fundamental research, is we're really trying to make something that may have a potential to be used in the real world. And also we have done some collaboration with YDOT. YDOT has provided some funding for this project as well. So obviously to get to this stage, where we can send samples to clients and they can do testing and do all these different things, we have to continue to develop and scale. And so Trina and the team at SCR, they're all working to build, to do all these scale-up portions. And so the next scale-up is doing this kind of pilot scale where you can make, several kilograms an hour in this plant here. So this is something that they built. It's a little bit, it's off from campus. You can go see it. You can ask Trina and her team, and they can show it to you. But it's pretty impressive, But we have to go to this scale, and we need to go to the scale so that we can understand what it's actually going to take to go to the next scale for commercialization. So on that pathway, you need to go to a demonstration plant. So there's 2 demo plants that are funded, and one is getting built. And it's you can see right here. Here's kind of a recent picture of that plant up by Gillette. So this plant here is kind of dealing with the different aspect. This is not necessarily the asphalt aspect, but the asphalt portion is funded. And so the pilot plant is there. We're using and learning everything from the pilot plant to do the final design and then do the construction of the one that will be used for making asphalt. So this was supposed to be completed in 26, but actually it'll be 2027. We're working with YDOT. They're going to pave some test sections up there around the Gillette area. And this plant, is going to have to run several days continuously to get that kind of material because we need 30 tons of binder to pave, like a mile section. So we have to go to pretty large scales here. So the other things that are being done, so that we make sure that we don't create any waste and, that we can create valuable, useful products during this whole thing is, what do we do with that 15 to 25% that is not going to go into the asphalt? Well, that can go into this other process, which is that plant that was already set up that's being built. But these are some of the things that have been developed already from coal that would be useful for that 15 to 25% that we're not using. So one is this of the char bricks. You may have seen this. This is on campus. There are these 2 houses. This was a DOE funded project. This is a conventional brick house, and then their char brick house. And so it's been out there for some years, seeing how it's weathering, how the bricks are behaving. But these bricks have a lot of great properties. They're lightweight, they insulate better, they have a way to recycle them. So there's a lot of advantages to this. The other thing is you can make soil amendments. So basically if you heat up that material, the same process that's being used to make those bricks, you create a char that is pretty porous and pretty pure. And so it's something that can be applied just like biochar to help soils retain moisture, add some nutrients, help in the growing of the plants. And so this is actually being used, and it's been tested in different situations, but actually being used to do some mine reclamation. And so there's some very large projects where they're using it already. So this is great that we have all these potential, not potential, but we have these different material outlets. So that last thing I just want to talk about, and I'll just touch on this briefly because I'm running out of time here, but there was a study done by the American Coal Council when they saw all of a sudden that coal was diving off, and they said, okay, well, what can we do new with coal? And they began to look at the whole coal refinery concept again and to begin to think about materials and other things. And so they said, what are things that are really attractive market-wise, meaning the size, the growth rate, and all these things, and what makes sense, because we can't compete, like if you want to make liquid hydrocarbon fuels, it probably doesn't make sense to use coal because you can do it with much less energy and more cheap from crude oil. So, it needs to be something that makes sense competitively. And so basically you go in that upper right-hand quadrant, and those are things that make sense market-wise and actually make sense for the material that you're dealing with. And so one of the areas that is very promising that could be a very high-growth area with a big impact is carbon fiber. And so carbon fiber is used in different applications. So, planes, wind turbine blades, electric cars, because we got to lower the weight, and and not lose strength and all of these things. But this is a market that's just been jumping, making huge jumps in demand. And in fact, the demand is so great that, you know, the supply just can't keep up with it. But you just see here, this is just saying basically from 2011 to 2026, you can see that there's been just a, you know, like a 7-fold increase in using this material. So to make carbon fiber, one of the traditional ways is to take coal tar pitch. You take coal tar pitch and you heat treat it, and what you see here, these little kind of spheres, these little bright colored spheres, that is a liquid crystalline phase that gets made in that heat treatment. You keep heating it and you make more and more of those spheres. Eventually you make so many, it's like an emulsion, it goes into a phase inversion and it becomes a continuous phase. This liquid crystalline phase is what you need to make good carbon fiber with high strength and high stiffness. So, and then on the bottom, these are the softening points. And so you can see that these materials, typically you melt spin to make a carbon fiber with pitch, and you have to get, you melt spin at like 300 degrees C. And so these are liquid crystalline phases, but at very high temperatures. So this is work that we had done with a DOE project. Oak Ridge National Laboratories was on this with a whole bunch of other people, and we made the mesophase pitch, they spun the carbon fiber. We were able to show that we can make carbon fiber that would meet the automotive industry demands for properties and also for cost from coal tar. So that's the other kind of main outlet that we're starting to investigate, because there is a little bit of liquid that's produced in all of these processes. So we want to make sure we use everything from the coal. So in the end, you know, is coal really this dirty thing that we should just leave it in the ground and forget about it? Well, coal, if you look at it from a material application standpoint, again, I'm not showing all the energy inputs and everything to make the final product, but as a raw feedstock, it actually makes a lot of sense. It has a very low carbon footprint. Solvent extraction, we found, is a really good way to utilize a huge amount of the coal to transform into high quality asphalt binders. And that, you know, we can, if we use fatty acids, then we can add additional benefits, which is to sequester CO2. And I already mentioned that this is one of the areas, you know, this is kind of dominating the economics, you know. It's not out of the picture to be economical, but if we could somehow get, you know, the price of fatty acids to come down to where they were 10 years ago, we would have no problem. Easy peasy. So the demonstration plant that does what's called the flash pyrolysis is where you make the bricks and the soil amendments and you get a little bit of liquid. That's already very advanced. It's being built, and we have all these real world examples already of the bricks being used and soil amendments being used in the field. And the demonstration plant for the solvent extraction, a lot of the infrastructure that's there for the pyrolysis plant is already being built so that the solvent extraction for the asphalt is going to plug right into all of that. So part of the solvent extraction, all that infrastructure, everything's already being put into place. The actual plant, you know, itself will come a little bit later. So depending on, you know, we're still studying the pilot plant, the Trina and Mark and all these guys, they're studying all of that so that we make sure that when we do the demo plant, everything is going to work well and give us the right product. Mesophase pitch and carbon fiber, you know, that this is something that we're looking at. We have seen evidence of being able to make mesophase pitch, and we need to refine that process even further. And in my opinion, and I hope in yours now, yes, PRB coal is something that's worth using for material-based applications. So with that, I just want to say thanks to SER for funding, and also can answer some questions for you.
Questions for Jeramie?
So I was thinking about that asphalt recycling process. So you said 5% is the binder, right?
Yep.
They grind it up. So presumably the new asphalt, it's hard to just cover it back up, right? Could you take a big iron and iron the old stuff in? I mean, presumably the binder is very stable, right?
Yeah, the thing is efficiently heating it and all these things. There's a company that has a technology where they actually have these large like microwave type things where they actually can heat it up and kind of remelt it. There's a lot of technologies out there. There's cold in place recycling where they actually have this kind of like combination of vehicles that goes through and it mills it up, and then it adds some other chemicals and makes some emulsion and does different things, and then it can lay it right back down. But yeah, I mean, to your point, yeah.
You don't foresee any big change in that would have an impact on the
Yeah.
demand, right?
Right. The push that people really look at is the cold in place recycling, just because the reality is, the amount of heat that you need to get your material up to, to get everything to flow back, you need to be up like in that 150, 160 C range. And so it's quite a bit of energy. And then the mass of all of that, you have to heat up all that, because the other 95% is all that, you have all that thermal mass of all that rock aggregate that needs heated up and everything, so.
More questions?
Thanks for a really good talk, Jeramie. I really enjoyed it. This is probably a dumb question, but you showed us the rheology as a function of the thermal properties. Do you have to look at it from like a shear stress or friction perspective, making sure that it wouldn't, I guess, degrade more rapidly with cars driving over it, trucks driving over it, that kind of mechanical behavior, so to
Yeah,
speak?
so there's the cohesion, the strength of the material, which is, how well it's going to hold together internally. And so there, in the paving world, we do have a test to do that. It's called the multiple creep recovery stress test. And so multiple stress, creep and recovery test. Thanks, Yogesh. So Yogesh is a civil engineer on our team, and so he deals with the rheology. I'm the chemist, so I'm a little bit dumb with the rheology. But yeah, so this is a test that sits there and you stress it, and then you let it relax, and then you do it again and do it again. And there are some thresholds that they have that you can weed out materials that have bad cohesive strength. But the thing is, in the asphalt industry is that they don't usually use, they still use a lot of binder like this, but a lot of it's polymer modified with styrene, butadiene, styrene. And in Wyoming, in fact, 95% of everything YDOT puts down is SBS modified. And so you can overcome a lot, some of these issues, just by doing what they're going to do anyway, which is polymer modification. But it is a concern. We actually did make early on, some of the early materials we made, they had bad cohesion properties, and so we spent a lot of time trying to do polymer modification and all this stuff. But the new materials that we have now, these are the ones that I'm confident in that are probably going to go forward to commercial production, and so they look really good.
Any other questions? So thank you, Jeramie, for your insightful presentation. If you're interested in learning more about either the asphalt binder that we're making or any of the other coal to products worked, contact us or talk to Jeramie. Just as a reminder, the next distinguished speaker presentation will take place Wednesday, March 4th, and feature Dr. David Anderson from Los Alamos National Laboratory, who will speak on nuclear modeling, providing an overview of LANL as well. Thank you. Have a great afternoon.